Today we are going to present our assignment 2, Automatic Flight Control System from Group 1. My name is Li Jiahui, matric number 203737. Introduction. Auto flight control system has their component parts divided into 3 major groups: sensor, amplifier, and output units. The signal were originated by the sensor as they are opened by outside reference. They only sense changes but do not make correction because the insufficient of power. The brain of AFCS is amplifier and computer. They receive the weight signal from the sensors, which in most cases are signs, and determine how much and in which direction correction is necessary. Most amplifier has at least 2 stages of voltage amplification. One stage of phase discrimination while another stage where power amplification takes place. The output unit is the master of the auto flight control system. It consists of an electro or hydraulic booster package. In a nutshell, the sensor sends a small signal to the amplifier or computer when displacement occurs. The amplifier or computer amplifies the weight signal to a workable voltage and sends it to the output unit. The output unit changes the electrical energy to mechanical displacement, so it then moves the control surface by an amount commanded by the sensor signal.
My name is Nurul Izzati binti Muhammad Izzat, and I will be presenting about the Automatic Flight Control Systems, which is AFCS components. So the first one is electric and electrical components. AFCS depends a lot on electric and electrical components. The control panel is used to allow any pilot desired operation that is within the capability of the system. Originally, AFCS systems were very limited because they were supplied with only one channel operation to the ailerons to keep the wings level. As more developed evolved, advanced aircraft receive signals from other aircraft systems which use the radar and barometric altimeter signals coupled with the AFCS to maintain the aircraft at a constant altitude. Some aircraft occupy signals from the data link systems to fly the aircraft during approaches and landings, while some fighters have the fire control system tied so the aircraft can fly automatically to an enemy aircraft in order to release weapons at a precise timing and accurate target. Next, which is the control panel. As you can see in the figure, that is the AFCS control panel. So all the switches and necessary controls for the pilot to control the autopilot mode are accessible on the AFCS control panel as shown in the picture. Each control panels are different for different types of aircrafts that serve different purposes, where it explains why some control panels are simple and some are complex. The next one is Air Navigation Computer, which is ANC. The Air Navigation Computer is where all the operating functions of AFCS are channeled through. This part is also known as the Amplifier Computer, which also known as the main cores of the entire system, meaning the entire system is depending on ANC. The ANC will modify the combined signals received by various sensors and command controls to produce output signals, where it controls the aircraft ailerons, rudder, and elevators. By using these flight controls, the aircraft automatically will maintain a reference altitude, heading, and altitude. Also, it can operate in a coordinated manner in response to turn and pitch control settings on the control panel. Next one is the control stick. As you can see in the picture, this is the control stick steering components. The control stick is used in aircraft to electronically control through AFCS. On fighters, the signals are generated in a unit such as the one labeled multi-channel pickup transducer, just like shown in the second picture. When the AFCS is on and the control stick is moved to the left or right, pressure on the roll force switch momentarily disengages the roll channel for the AFCS. The pilot then control the roll attitude of the aircraft through the regular stick control. When the pilot releases stick pressure, the force switch opens, allowing the AFCS to re-engage roll. If the bank angle is above the given angle, the AFCS will maintain the bank angle. If the bank angle is below the given angle, the AFCS automatically returns to the wing level. The pitch force switches close when a force pressure is on the control stick. This action momentarily disengage the AFCS. That is it. Continue to the next presenter.
My name is Bobby Yu Chung Leong. My metric number is 203246. Now I will be presenting for electric and electronic sensors. The first one will be signal generator peacock synchro. So the peacock consists of stators and rotors. So a stator is a ring-shaped and has 4 poles. Each pole will consist of primary and secondary winding. So it can change the reluctance of the magnetic flux path. So when primary and secondary winding are connected, the voltage that induced in adjacent pole will be of opposite polarity, but for the opposite pole, it will of same polarity. So rotor, the output of the rotor will be equal to 0 if it is in neutral position. So the greater the displacement of the rotor, so the greater the amplitudes. So the next one will be gyros. There are 2 gyros. So the first one will be vertical gyros. It is an electrically driven gyro. So it provides pitch and bend attitude for FCS. So it is also an 2 degrees of freedom gyros. It will continuously erect with its spin axis vertical to the surface of the Earth. So the spin axis will provide the vertical reference for measurement of aircraft bend angle and pitch angle. So the next gyro will be the 3-axis rate gyro. So this gyro will sense the rate of movement of the aircraft in vertical, lateral, or longitudinal axis. It also provides signal output representing yaw rate, pitch rate, or roll rate to the air navigation computer. So it can measure the angular rates if there is torque generated by rate of movement about the gyro sensitive axis. So the next sensor will be compass information. So the compass system will incorporate a gear train to drive the several synchros. So the synchros will provide the heading information to the pilot's compass indicator. It also can provide the clutch heading. When AFCS is not engaged, the clutch will remain de-energized. But if the AFCS is engaged, the clutch will be engaged and establish a reference heading. So the next one will be the data information. There are 2 data information. The first one will be the airspeed. So it will control the gain control unit will modify the control surface signal, and the unit is will use the difference between the ram pressure and static pressure. So if there is increase in the airspeed, the spring will be more compressed and it will modify the control surface signal. For the altitude, it will maintain the aircraft at the fixed altitude. There is aneroid mechanism for transmitting and magnifying the motion of the aneroid and a solenoid operated clutch. The next one will be flag position information. So when the flag is lower, the increased lift will cause the aircraft gain altitude, which is ballooning. So when AFCS is engaged, the automatic north-south force is applied to elevate better. So the flag position is detected by the flag position transmitter. Following by is accelerometer transmitter. So it will generate the signal proportional to normal vertical acceleration. So the sensitive element will assembly has peacock, armature support, fascia, spring, and back plates. When it is assembled, the sensitive element assembly and below shielded inside a housing with damping fluid. So it will allow the volume of the damping fluid to change with temperature and pressure variation. And the next one will be, and the last one will be the coordinates inputs. So the dynamic vertical sensors will detect the lateral acceleration of the aircraft. So the sensor will supply signal to position the rudder and also provide a signal output of the condition of split or skip resulting from lateral acceleration.
Hi, my name is Lim Jyotin and my matrix number is 203245. So, as for my part, it's about hydraulic components. Okay, so first of all, what is a hydraulic system? A hydraulic system is a drive technology where a fluid is used to move the energy from an electric motor to an actuator, such as a hydraulic cylinder. This fluid is uncompressible and the flow path is flexible in the same way as the electric cable. Hydraulic systems are mainly used in mobile equipment, and also because of the simplicity coming from using few components to obtain complex and fast-moving machines with a high degree of safety. Okay, so in an automatic flight control system, there are electro-hydraulic actuators. So what does they do? They provide the physical power to move the flight control surfaces. So there are two types of electro-hydraulic actuators. The first type is electro-hydraulic servo actuators, and the second type is automatic trim. Okay, electro-hydraulic servo actuator. Okay, there are two modes for this, which is the manual mode and the other one is called electric, but I will focus on manual mode first. So manual mode, what is it? What is it used to? It is to aid the pilot in manually positioning the control surfaces, and also the hydraulic booster package is connected between the pilot's control stick and the control surface in the manual mode of operation. So on large aircraft, the control surface is much too large to move unaided, whereas the smaller and high-speed aircraft has high air pressure, which makes it nearly impossible to move the control if it's unaided. Okay. The figure below is the conventional linear actuator. Okay, the second mode is the electrical signals, as I mentioned before. So the booster package connects the automatic flight control system and provides the power to move the surface. Okay, below is a block diagram of hydraulic booster. So, okay, start from the surface position. So the surface position transmitter on the top right here sends signals representing the amount of direction of control surface displacement from the streamline position. This is to prevent overshoot of the control. Okay, next, when the control surface is in motion, when it reaches here, okay, the modulating piston is displaced. The system will monitor the position of modulating piston to detect the control surface rate of movement. Subsequently, this action generates a signal to the damp control surface movement. Next, when it moves and it moves up to here, the hydraulic load sensor detects and calculates the amount of pressure the automatic flight control system is applying to the control surface. This is to allow the pilot to properly trim the aircraft before disengaging the flight control system. The trimming procedure is very important to keep the stability of the aircraft. That's why it's very important. Okay, next. This is the second type of electro-hydraulic actuators, which is automatic trim. So, okay, this is also a block diagram of automatic pitch trim. Some automatic flight control system incorporates automatic trimming. Whenever a signal is present in the control channel, there is an unbalance in fluid pressure at the input of hydraulic booster, which is this one up here. The hydraulic load sensor will then amplify the signal and drives the trim servo motor, which is towards here. The engagement clutch engages when the automatic flight control system is operating as well as the automatic trim is functioning properly. The function of the slip clutch here, slip clutch, is to allow pilot to override the automatic trim in case of malfunction occurs. Most automatic flight control systems use auto trim to pitch channel. However, it is also to be used for yaw and roll as well. So that's all for my part. I will pass it to the next presenter.
So now I will be explaining the theory of operation for the AFCS components. So I will be explaining the theory of operation for AFCS component. So this is the basic AFCS control channel, as you can see on the screen. So the air navigation computer, or known as ANC, receive various error and control signals. These weak signals are coupled, or you can say it was summed, modified and amplified to develop the control surface command signal to drive the electro-hydraulic actuators. The actuators move a certain direction for a specific distance depending on the command signal's polarity and magnitude. The flight control surfaces, such as rudder, aileron, and elevator, are mechanically linked to the electro-hydraulic actuators. As the control surface moves, a position transmitter synchronizes develop a feedback signal having the opposite polarity to the error signal. The magnitude of the feedback signal increases as the control surface displacement increases. When the error signals and feedback signals are equal and opposite in magnitude and polarity, the control surface will no longer move. Movement of the control surface causes the aircraft to displace about its axis or its own reference, which this movement corrects the original error signal as sensed by the sensors. Without any error signals inputs to the control channel of the amplifier computer, only the feedback signal is present. The feedback signal is opposite in polarity and magnitude to the original signal. This drives the electro-hydraulic actuators an equal distance in the opposite direction and brings the control surface back to the null for reference position.
Auto flight control system modes. First, stability augmentation mode. The stability augmentation mode provides improvement control of the aircraft by automatically damping oscillation about the low, yaws, and pitch axis. The surface movement controlled by the signal from the red gyroscope commands through the electro-hydraulic actuator. The stability augmentation is considered critical to save flight in some high-speed aircraft. Second, attitude hold. The attitude hold mode is the basic and the hands of the mode of operation. The AFCS maintains the aircraft attitude at the time engagement in the peak and low with attitude hold mode engaged. This particular mode is governed by the actual degrees of bank of pitch of the aircraft. Third, altitude hold. The aircraft will maintain the altitude at the time engagement with the altitude hold engaged. The aircraft returns to the altitude that exists at engagement if the aircraft is climbing or diving at engagement. The AFCS receives control signal from this mode from the ADC. Fourth, heading hold. The AFCS maintains aircraft heading at the time of engagement with heading hold engaged. 3. Control stick steering. The control stick steering mode lets the pilot manually change the attitude of the aircraft. AFCS engaged without disengaging it. After adhering to new attitude, the pilot releases the stick and the AFCS resumes control the aircraft. 6. Heading select. The aircraft will automatically turn to a course selected by the pilot. The aircraft will assume a fixed maximum roll and turn to the selected heading open engagement. 7. Mesh hold. This function maintains the mesh number existing at the time of mesh hold engagement. 8. Automatic Carrier Landing System ACLS. In this mode, the pilot can make a hand-off carrier landing. The aircraft will throw command signal generated by the data link receiver. Ground control bombing. The aircraft follows the command signal from the personnel on the ground. Thank you.
Hi, my name is Muhammad Yunus bin Shamsul Bari. My matric number is 204686. So now I will talk about autopilot systems in automatic flight control systems, or AFCS. So the autopilot concepts. So many advanced avionic installations include two different integrated systems, such as the autopilot system, which is the set of servo actuators that do the control movement, and the control circuits to make the servo actuators move correctly for their designated task. The second is the flight director component, which is basically the brain of the autopilot system and sends signals to the control circuits to move the servos based on the information they receive from other instrumentation in the cockpit. Autopilots can automate tasks such as maintaining an altitude, climbing or descending to an assigned altitude, turning to and maintaining an assigned heading, intercepting the course, guiding the aircraft between waypoints that make up a route program into an FMS, and flying a precision or non-precision approach. So how do autopilot functions work? Once an autopilot mode has been engaged from the cockpit, the autopilot determines which control movements are required to follow the flight profile entered by the pilot and moves the controls to effect tracking of the flight profile. So, once the autopilot is on, how does the determination of control movements is it required to achieve the goals? So, let's assume or suppose you wish to use the autopilot to turn to an assigned heading of 270 degrees. So before any control movements are made, the autopilot or flight director must first determine which control movements are necessary. For example, maybe the plane has to turn left or to turn right. So to do so, the flight director gathers and processes information from the aircraft's ABC or airspeed and altitude. The magnetic heading reference instrument and navigation systems are also referenced, and the FD gathers and processes this information. So the flight director or autopilot then determines the aircraft's current heading and bank angle. It then determines the amount and direction of the turn, and finally chooses an appropriate bank angle, usually up to 30 degrees or less. So carrying out control movements, now that it has determined what kind of movements is required to achieve the goal, it now has to carry out the control movements. So once the flight director has determined which control movements are necessary to achieve the flight change, the autopilot has the task of carrying out these control movements. So every autopilot system features a collection of electromechanical devices called servos that actuate the aircraft control services. These servos translate electrical commands into motion, also known as the muscle that actually moves the control service. So that's it for my part of the presentation. Now I'll pass the video to Mims to complete the conclusion and complete our presentation.
Okay, so we have reached the conclusion of this presentation. So in conclusion, Automatic Flight Control System or AFCS play an important role in the avionics of modern day aircraft. Not only do they provide relief to the pilots by introducing automation on an aircraft, AFCS also allows them to focus on more important tasks such as communications, navigations, and special equipment. AFCS also provides a layer of safety on all aircrafts from subsonic to supersonic speed with improved stabilization, crosswind correction, and many more features. Furthermore, AFCS is constantly being improved by manufacturers to be able to handle more and more tasks simultaneously than a pilot could ever handle. However, regardless of how sophisticated AFCS computers may be, the reasoning power of a pilot cannot be duplicated. As such, there must always be a pilot behind all the controls. So, thank you for watching.